At the dawn of the 20th century, physics encountered a crisis that no amount of refinement could resolve. Experiments began to reveal behaviors in light and matter that simply did not fit within the elegant structure of classical laws. Light, long understood as a wave spreading smoothly through space, suddenly behaved like a stream of discrete particles when it struck metal surfaces or left sharp marks on photographic plates. Matter, assumed to be solid and localized, displayed interference patterns as if it were a ripple on water. These were not minor anomalies. They were deep contradictions that forced science to confront an uncomfortable truth: reality itself could not be captured by a single, intuitive picture. What made this realization so revolutionary was not just the strangeness of the results, but their consistency. Whenever scientists designed experiments to detect wave-like properties, they appeared unmistakably. When the same systems were tested for particle-like behavior, the wave description vanished and particles took center stage. No experiment ever showed both aspects fully at the same time. This was not a failure of technology or experimental design. It was a fundamental feature of nature. The universe seemed to demand two mutually exclusive descriptions, each correct in its own context, yet incompatible when forced together. This was the intellectual landscape in which Niels Bohr introduced one of the most radical ideas in the history of science. Bohr recognized that the mistake lay not in the experiments, but in the assumption that reality must conform to a single coherent image. Classical physics had trained generations of scientists to believe that a physical system must possess definite properties at all times, independent of how it is observed. Bohr challenged this assumption at its core. He proposed that wave and particle descriptions are not competing explanations, but complementary ones. Each reveals something real, yet each excludes the other. In this view, reality is not a fixed picture waiting to be uncovered. It is revealed through interaction. When we design an experiment to measure position, we inevitably destroy information about momentum. When we set up an apparatus to observe interference, we lose the ability to track individual particles. The properties we observe are inseparable from the questions we ask and the tools we use. This was a profound shift. Observation was no longer a passive act of recording what already existed, but an active process that participates in shaping what can be known. This idea struck many as deeply unsettling. It seemed to undermine objectivity itself. Yet Bohr argued that objectivity was not lost, it was redefined. Objectivity did not mean describing nature as it is, in itself, independent of all conditions. It meant clearly specifying the experimental context and the limits within which statements about reality are valid. Precision, not certainty, became the new standard of truth. The wave and particle pictures were both necessary, but neither was complete on its own. As the implications of this insight spread, it became clear that the problem was not limited to light or electrons. It touched the foundations of knowledge. Human intuition evolved in a world of solid objects moving at moderate speeds, not in a realm where energy arrives in quanta and observation alters outcomes. Expecting microscopic reality to obey macroscopic intuition was an unjustified assumption. Bohr's genius lay in recognizing that understanding nature sometimes requires abandoning the demand for a single, comfortable explanation. This acceptance of dual description marked a turning point. Instead of asking which picture was really true, physicists began asking under what conditions each picture applied. This change in perspective unlocked extraordinary progress. It allowed quantum mechanics to develop into a powerful predictive framework without resolving its philosophical tensions. The theory worked not because it removed paradox, but because it learned to live with it honestly. In the second half of this realization, the deeper consequences began to emerge. If wave and particle descriptions are both necessary, then reality itself resists being fully captured by language or imagery. Words like wave and particle are borrowed from everyday experience, yet at the quantum level they are only metaphors. They point toward behaviors, not substances. Bohr emphasized that these concepts are tools, not mirrors of nature. Their usefulness lies in what they allow us to predict and communicate, not in their ability to represent an underlying essence. This perspective introduced a new humility into science. Instead of assuming that the universe must make sense according to human categories, Bohr suggested that our categories must remain flexible. Knowledge becomes a dialogue between the observer and the observed, constrained by the conditions of measurement. There is no contradiction in using two incompatible descriptions, as long as each is applied within its proper domain. The contradiction only arises when we demand more from a single description than it can give. This way of thinking reshaped scientific reasoning itself. It taught that completeness does not always mean unification. Sometimes completeness requires multiple, limited viewpoints that cannot be merged without loss. This lesson extended far beyond physics. It influenced how thinkers approach problems in philosophy, psychology, and even ethics, where complex phenomena often resist simple explanations. By accepting that reality can legitimately appear in different, mutually exclusive ways, Bohr offered a framework that was both intellectually rigorous and deeply realistic. He did not claim that the universe was illogical. He claimed that human logic, shaped by everyday experience, was insufficient on its own. The future of science, he believed, depended on the courage to accept this limitation. In embracing the necessity of both wave and particle descriptions, Bohr did more than solve a technical problem. He redefined what it means to understand. Understanding was no longer the elimination of mystery, but the disciplined recognition of where mystery is unavoidable. This insight continues to shape modern physics, reminding us that reality is richer, subtler, and more demanding than any single story we can tell about it. As this way of thinking matured, its consequences became impossible to ignore. Accepting that reality reveals itself differently depending on how it is questioned forced scientists to reconsider what they meant by explanation itself. An explanation was no longer a single picture that replaced ignorance with clarity, but a framework that respected limits. The wave description explained interference and diffraction with astonishing accuracy. The particle description explained detection events, energy exchange, and localization just as precisely. Each description answered questions the other could not. Together, they formed a complete account, not by merging, but by coexistence. What made this so difficult to accept was the human desire for visual certainty. Classical physics allowed one to imagine tiny balls moving along well-defined paths or continuous waves spreading smoothly through space. Quantum phenomena refused such comfort. Attempts to force electrons to behave like miniature planets or light to behave like ordinary ripples led to contradictions. Bohr insisted that this discomfort was not a sign of failure, but a sign that intuition had reached its limit. Nature was not obligated to be imaginable, only to be consistent. This insight had practical consequences. Experimental design itself became an act of choice. To observe one aspect of a system meant deliberately giving up access to another. This was not an unfortunate side effect, but a defining feature of reality at small scales. Precision in one measurement required sacrifice in another. The universe imposed a kind of balance, ensuring that no experiment could extract a complete, all-encompassing picture. Knowledge arrived in fragments, each sharp and reliable, yet never total. Over time, this approach proved extraordinarily fruitful. Quantum mechanics, built on these principles, produced predictions of unprecedented accuracy. Technologies based on it transformed the world, from electronics to lasers to modern computing. None of this required resolving the underlying paradox. The theory worked because it respected the rules set by nature rather than insisting on philosophical comfort. The acceptance of dual descriptions became a strength, not a weakness. Yet the deeper philosophical implication remained unsettling. If physical reality itself demands mutually exclusive descriptions, then certainty has limits not just in practice, but in principle. Bohr argued that this was not a retreat into relativism. It was a disciplined realism, one that acknowledged that statements about nature are always tied to the conditions under which they are made. Truth remained objective. but never detached. It always carried the imprint of the experimental context. This idea quietly transformed how scientists spoke about reality. The language of physics became more careful, more precise, and more modest. Claims were no longer absolute but conditional. Instead of asking what an electron really is, physicists asked how it behaves under specific conditions. This shift avoided endless metaphysical disputes and focused attention on what could be tested and communicated clearly. In this sense, Bohr's contribution extended beyond physics into the very structure of human understanding. He showed that contradiction does not always signal error. Sometimes it signals depth. When two descriptions cannot be combined, it may be because reality itself is richer than any single viewpoint. Progress, then, does not come from choosing one and rejecting the other, but from learning when and how each applies. By embracing this disciplined acceptance of limits, science gained a new kind of power. It learned to move forward without demanding final answers to every philosophical question. It learned that understanding can grow even when mystery remains. This legacy continues to guide modern physics, reminding us that the universe is not a puzzle to be flattened into simplicity, but a structure that reveals itself layer by layer, depending on how we choose to look. At the turn of the 20th century, the triumph of classical physics appeared complete. The laws of motion and electromagnetism described the visible universe with astonishing success, from the paths of planets to the behavior of machines. Yet beneath this confidence, cracks were forming. When scientists pushed their instruments to probe the atom, the old rules began to collapse. Matter did not behave like miniature versions of everyday objects. Instead of stability, there was instability. Instead of continuity, there were sudden jumps. Instead of certainty, there were contradictions that no refinement of existing theory could repair. One of the most troubling failures involved the atom itself. According to classical reasoning, electrons orbiting a nucleus should radiate energy continuously and spiral inward, leading to the rapid collapse of atoms. But atoms were stable. Matter existed. This single fact exposed a fatal flaw in the classical picture. Another breakdown emerged in the study of light emitted by heated objects. The predicted energy distribution diverged wildly from experimental results, producing infinities that had no physical meaning. These were not small errors. They signaled that the conceptual foundation of physics was inadequate at microscopic scales. In this moment of crisis, Sir Niels Bohr recognized that the problem could not be solved by adjusting equations alone. The failure was deeper. Classical physics was built on assumptions about continuity, determinism, and precise trajectories, assumptions rooted in everyday experience. Bohr understood that insisting on these ideas inside the atom was like demanding that shadows behave like solid objects. The rules that governed the macroscopic world were being applied where they no longer belonged. Bohr's response was radical because it was selective. Instead of discarding classical physics entirely, he preserved it where it worked and restricted it where it failed. He proposed that atomic systems could exist only in specific, allowed states, and that transitions between these states occurred in discrete steps. Energy was not a smooth flow but came in packets. This was not derived from classical reasoning, it was imposed to match reality. The success of this move revealed a shocking truth: nature itself was quantized. What made this revolutionary was not just the introduction of discrete energy levels, but the acknowledgement that classical descriptions break down at a fundamental boundary. Inside the atom, familiar concepts like precise position and continuous motion lose their meaning. They cannot be applied without contradiction. Bohr treated this not as a temporary limitation of knowledge, but as a structural feature of reality. There existed a domain where classical language could no longer speak accurately. This realization demanded intellectual courage. For centuries, physics had advanced by extending classical ideas into new territories. Bohr showed that progress sometimes requires stopping, drawing a line, and admitting that a trusted framework has reached its limit. The atom was not a smaller version of the solar system. It was something entirely different, governed by principles that had no counterpart in everyday experience. By accepting the failure of classical physics at small scales, Bohr opened the door to a new way of thinking. Instead of forcing nature into inherited concepts, he allowed experimental evidence to dictate which ideas survived and which had to be abandoned. This shift marked the true beginning of modern physics. It was the moment science learned that its most powerful tools could also become obstacles, and that recognizing their limits was not weakness, but the first step toward deeper understanding. As this new perspective took hold, its implications spread rapidly through the foundations of science. Accepting that classical physics fails at microscopic scales meant accepting that determinism itself was no longer guaranteed. The idea that the future of a system could be predicted with absolute certainty, given complete knowledge of its present state, began to erode. At the atomic level, the very notion of a well-defined trajectory dissolved. Events occurred not as smooth evolutions, but as transitions between allowed states, governed by probabilities rather than certainties. This shift was deeply unsettling because determinism had been more than a technical assumption, it was a philosophical cornerstone. For generations, scientists believed that unpredictability reflected ignorance, not nature itself. Bohr's framework suggested something far more radical. Even with perfect experimental control, there would remain limits to what could be known and predicted. These limits were not due to human imperfection, but to the structure of reality. The universe, at its most fundamental level, did not operate like a clockwork mechanism. What made this acceptance possible was the clarity with which classical and quantum domains were separated. Classical physics did not become false, it became conditional. It remained extraordinarily accurate for large systems, where quantization effects average out and uncertainty becomes negligible. But when applied beyond its domain of validity, it produced nonsense. Bohr emphasized that understanding required knowing not only how a theory works, but where it stops working. This distinction preserved the power of classical laws while freeing physics from their tyranny. As quantum theory matured, this boundary between classical and non-classical descriptions became a central concern. Measurement devices themselves had to be described in classical terms in order to communicate results. Yet the systems being measured obeyed quantum rules. This created a conceptual tension that could not be eliminated, only managed. Bohr argued that this tension was unavoidable and even necessary. It reflected the fact that human knowledge depends on classical concepts, even when nature itself transcends them. This approach changed how scientists evaluated theories. Success was no longer measured by how intuitively satisfying a model felt, but by how accurately it accounted for observations within clearly defined limits. A theory could be profoundly counterintuitive and still be correct. In fact, at the quantum level, counterintuitiveness became a warning sign that one was finally approaching the truth rather than clinging to familiar illusions. Over time, this way of thinking proved transformative. It allowed physics to move forward without resolving every philosophical discomfort. Instead of demanding a single, unified picture of reality, scientists learned to work with layered descriptions, each valid in its own range. This flexibility fueled rapid progress, leading to advances that reshaped technology and society. By confronting the failure of classical physics honestly, Bohr helped science mature. He showed that progress does not come from defending old certainties, but from recognizing when they no longer apply. In doing so, he redefined the relationship between theory and reality, teaching that the deepest truths are often found not in what our theories explain, but in where they finally admit their own limits. The realization that nature is not continuous, but structured in discrete steps marked one of the most profound breaks with classical thought. For centuries, physics assumed that change happened smoothly, that energy could be divided endlessly into smaller and smaller amounts, and that motion flowed without interruption. This assumption worked perfectly in the visible world, where transitions appear gradual and differences blend seamlessly into one another. But when scientists turned their attention to the microscopic realm, this comforting continuity began to fracture. The first signs appeared in the study of light and heat. When objects were heated, they emitted radiation in patterns that defied classical prediction. Instead of producing energy across a smooth range of frequencies, nature favored specific values. Attempts to explain this behavior using continuous models failed catastrophically, leading to infinities that had no physical meaning. The conclusion was unavoidable: energy exchange at small scales did not occur in arbitrary amounts. It happened in fixed units. This idea challenged intuition at every level. To suggest that energy came in indivisible packets was like claiming that a flowing river moved in jumps rather than currents. Yet experiments left no alternative. When atoms absorbed or emitted light, they did so at sharply defined frequencies. There were no in-between states, no gradual transitions. Something fundamental was being revealed about the architecture of reality itself. Within this emerging picture, Niels Bohr recognized that discreteness was not an inconvenience to be explained away, but a central principle to be embraced. His atomic model placed electrons in specific allowed states, each associated with a precise energy. These states were not chosen arbitrarily, they were dictated by the internal structure of the atom. An electron could exist in one state or another, but never between them. Change occurred through sudden transitions, accompanied by the emission or absorption of energy in exact amounts. What made this so revolutionary was that it redefined stability itself. In classical physics, stability required balance through continuous motion. In the quantum world, stability emerged from restriction. By limiting what was allowed, nature prevented collapse. Atoms endured not because electrons followed smooth paths, but because most paths were forbidden. The rules of existence were written not in terms of what could happen, but in terms of what could not. This discrete structure extended beyond atoms. It appeared wherever energy and matter interacted at fundamental levels. Vibrations were quantized. Angular momentum came in fixed units. Even the exchange of light followed strict numerical rules. The universe, it seemed, was built more like a staircase than a slope. Each step was precise, unavoidable, and deeply woven into the fabric of reality. Accepting this required a dramatic shift in thinking. Continuity had been synonymous with realism. Discreteness felt artificial, imposed, almost mathematical rather than physical, yet nature consistently favored it. The lesson was humbling: reality did not owe coherence to human intuition. Mathematical abstraction, once seen as a tool for describing the world, now appeared to reveal its deepest structure. In this new view, numbers were no longer just measurements of quantities, they were expressions of possibility itself. The allowed values defined what could exist. Everything else was excluded. The universe operated not as an open continuum, but as a system governed by selection rules, boundaries, and limits that were invisible at large scales but absolute at small ones. This understanding marked a turning point. It showed that the apparent smoothness of the world was an illusion born of scale. Beneath it lay a granular order, precise and unforgiving. By uncovering this hidden discreteness, physics began to glimpse a deeper layer of reality, one in which existence itself unfolds not as a blur of possibilities, but as a sequence of sharply defined truths. As this discrete picture of nature became clearer, its consequences spread far beyond atomic structure. Quantization was no longer a curious feature of isolated systems, it emerged as a universal principle shaping how reality organizes itself. Wherever interactions occurred at fundamental scales, nature enforced rules that allowed only certain outcomes. What appeared continuous at the human level was revealed to be an approximation, a statistical smoothing of countless tiny steps taking place beneath perception. This realization transformed the meaning of physical law. Laws were no longer instructions describing smooth evolution, but constraints defining which states were permitted and which were forbidden. Change happened not by gradual adjustment but by transition. Between one allowed state and another, nothing existed that could be observed or measured. The gaps were not empty spaces waiting to be filled, They were absences built into reality itself. This was a profound departure from classical causality, where every intermediate state was assumed to exist, whether observed or not. With quantization came a new understanding of energy exchange. Emission and absorption were no longer processes spread over time, but events. When a transition occurred, energy appeared or disappeared in exact amounts, instantaneously at the scale of the interaction. This event, like nature of change, challenged the classical image of time as a smooth flow. At the smallest scales, time itself seemed to be marked by moments rather than continua, reinforcing the sense that discreteness was woven into the structure of existence. The practical success of this idea was undeniable. Spectral lines could be predicted with astonishing accuracy. Chemical behavior became intelligible in terms of electronic structure. Stability, reactivity, and bonding all traced back to quantized states. What had begun as a desperate attempt to save atomic theory became the foundation of modern chemistry and materials science. None of this required imagining electrons as tiny objects following precise paths. What mattered were the allowed states and the rules governing transitions between them. Yet the philosophical implications remained unsettling. If reality at its core is discrete, then continuity is not fundamental but emergent. The smoothness of motion, the flow of energy, even the apparent solidity of matter arise from underlying structures that are sharply defined and limited. This inverted centuries of intuition. Instead of building complexity from smooth foundations, nature built smoothness from constraints. This perspective also reframed the relationship between mathematics and reality. Numbers and equations were no longer mere descriptions layered onto nature after the fact. They appeared to be embedded in the way the universe operates. The fact that only certain numerical values were allowed suggested that mathematics was not just a language invented by humans, but a reflection of deep structural rules. Reality behaved as if it were written in discrete symbols rather than continuous strokes. By embracing quantization, physics accepted that existence itself comes in steps. This acceptance did not diminish understanding, it sharpened it. It allowed scientists to stop searching for non-existent intermediates and to focus instead on the rules that govern allowed change. In doing so, it revealed a universe that is not vague or approximate at its core, but precise, selective, and exacting. This legacy endures in every modern theory that builds on quantum foundations. It reminds us that what seems continuous and obvious may be the product of hidden structure, and that the deepest truths often lie not in what changes smoothly before our eyes, but in the silent rules that decide when change is permitted at all. As quantum theory advanced, one of its most unsettling revelations emerged not from equations alone, but from the act of observation itself. For centuries, science had operated under a quiet assumption that nature exists independently of our attempts to measure it. Instruments were thought to record reality, not interfere with it. The observer stood outside the system, watching passively as events unfolded. This assumption worked flawlessly in the classical world, where measurements could be made without noticeably altering the system being measured. At the quantum scale, however, this separation collapsed when scientists attempted to observe atomic and subatomic phenomena. They discovered that measurement could not be disentangled from outcome. To determine the position of an electron required an interaction that disturbed its motion. To measure its energy altered its temporal behavior. Every attempt to extract information involved an exchange that changed the system in an irreversible way. This was not due to crude instruments or experimental error. It was a fundamental constraint imposed by nature. Within this emerging understanding, Arter's Niels Bohr articulated a radical shift in perspective. He argued that physical properties do not exist in isolation from the conditions under which they are measured. Position, momentum, energy, and time are not intrinsic attributes waiting to be revealed. They are defined through specific experimental arrangements. Change the arrangement, and the very meaning of the property changes with it. Reality at the quantum level is inseparable from the context of observation. This insight reframed the role of the observer. The observer was no longer a detached spectator, but a participant. The choice of what to measure shaped what could be known. This did not imply that consciousness created reality, a common misunderstanding that Bohr explicitly rejected. Instead, it meant that the physical interaction between measuring device and system was unavoidable. Measurement was an active process governed by physical laws, not a neutral window onto a pre-existing world. The implications were profound. If properties depend on measurement context, then asking what a quantum system really is, independent of observation, becomes meaningless. The question itself assumes a classical picture that no longer applies. Bohr insisted that meaningful statements about nature must always include a description of the experimental setup. Without that context, words like position or energy lose their operational meaning. This perspective challenged deeply held intuitions about objectivity. Many feared it reduced physics to subjectivity. Bohr countered that objectivity was preserved through precise communication of experimental conditions. What was abandoned was not objectivity, but the illusion that reality could be fully described without reference to how knowledge is obtained. Objectivity became contextual rather than absolute. As this view gained acceptance, it clarified long-standing paradoxes. Phenomena that seemed contradictory under classical assumptions became coherent once the role of measurement was acknowledged. The apparent randomness of quantum outcomes was no longer a sign of incomplete theory, but a reflection of fundamental limits on what could be predicted. Probability entered physics not as a temporary placeholder for ignorance, but as a basic feature of how nature behaves. This shift also altered the goals of scientific explanation. Instead of seeking a hidden mechanism behind every outcome, physicists learned to describe the conditions under which certain results could occur and the probabilities associated with them. Explanation became about structure and constraint rather than deterministic cause. This was a quieter, more disciplined form of understanding, but no less powerful. By recognizing that observation participates in reality, quantum theory redefined the boundary between the knower and the known. Bohr's insight did not diminish science. It strengthened it by aligning its methods with the true nature of the phenomena it studied. The universe, it revealed, is not a stage on which events play out independently of inquiry, but a system in which knowledge arises through interaction. This realization continues to shape modern physics, reminding us that understanding is not the act of standing outside reality, but of engaging with it under clearly defined conditions. One of the most challenging lessons to emerge from modern physics is that truth does not always arrive as a single, unified statement. In the classical worldview, contradiction was a sign of failure. If two descriptions disagreed, one had to be wrong. Science advanced by eliminating paradox, replacing it with clearer and more consistent explanations. This method worked brilliantly for centuries, reinforcing the belief that reality itself must be internally consistent in a way that human logic could fully capture. The quantum revolution shattered that assumption. As experiments probed deeper into the structure of matter, physicists encountered results that could not be reconciled within a single coherent picture. Light behaved as a wave in some situations and as a particle in others. Matter exhibited the same dual behavior. Attempts to force these phenomena into one category or the other led to logical dead ends. The paradoxes were not accidental, they were persistent, reproducible, and unavoidable. Reality itself seemed to speak in mutually incompatible terms. It was in this context that Niels Bohr introduced a way of thinking that redefined what scientific truth could mean. Rather than treating paradox as an error to be resolved, Bohr treated it as a clue. He argued that nature was not contradicting itself, it was exposing the limits of the concepts inherited from classical physics. The contradiction existed not in reality, but in the demand that reality conform to a single, all-encompassing description. This view required a profound shift in intellectual attitude. Instead of asking which description was correct, Bohr asked under what conditions each description was valid. Wave and particle pictures were both true, but not simultaneously applicable. Each revealed a real aspect of nature, yet each excluded the other. Truth, in this sense, was not absolute in form, but conditional in expression. It depended on context without becoming arbitrary. Accepting this kind of truth was deeply uncomfortable. Human reasoning is built to resolve ambiguity, not to preserve it. Paradox feels like a failure of understanding, yet quantum experiments repeatedly confirmed that insisting on resolution destroyed accuracy. When physicists accepted paradox as fundamental, predictions improved. When they rejected it, theories failed. This reversal forced science to reconsider the relationship between logic and reality. The paradoxical nature of quantum truth did not mean that anything goes. On the contrary, it imposed strict discipline. Each description had precise rules governing when it could be used. Misapplying a concept led to nonsense. The wave picture could not explain detection events. The particle picture could not explain interference. Understanding meant knowing the limits of each and respecting the boundaries nature imposed. Paradox was not confusion, it was structure. This approach transformed scientific language. Words like "as" and "has" became less absolute. Instead of claiming that a system possesses a property at all times, physicists described how that property manifests under specific conditions. The language of certainty gave way to the language of conditional statements. This was not a retreat from rigor, but an increase in it. Precision replaced simplicity. The broader implication was philosophical. If the most successful physical theory requires mutually exclusive descriptions to be true, then the idea that reality must be expressible in a single logical framework is an assumption, not a necessity. Nature may be internally consistent without being fully representable by one perspective. Truth, then, is not always something that can be flattened into one statement. Sometimes it exists only across a tension between statements. This lesson extends beyond physics. Complex systems, whether biological, psychological, or social, often resist simple explanations. Attempts to force them into a single narrative can distort more than they clarify. The quantum experience suggests that depth often appears where explanation becomes layered rather than unified. Contradiction, when carefully constrained, can be a sign of completeness rather than error. By accepting paradox as an intrinsic feature of reality, modern physics gained a new kind of honesty. It stopped pretending that understanding meant eliminating mystery. Instead, understanding became the ability to navigate mystery without distorting it. Bohr's legacy lies not only in what he explained, but in how he taught science to live with what cannot be fully reconciled. In this view, truth is not weakened by paradox, it is strengthened. It reflects a universe that is richer than any single description and more demanding than any one logic. The willingness to accept this complexity marked a turning point in human knowledge, reminding us that the deepest insights often begin where certainty ends. As the quantum view of nature settled into scientific practice, it quietly altered how certainty itself was understood. For centuries, knowledge had been measured by how precisely outcomes could be predicted. If the present state of a system was known in enough detail, its future was assumed to be fixed. This belief was not merely technical, it shaped how humanity understood causality, responsibility, and control. The quantum framework challenged this belief at its foundation by revealing limits that no refinement of measurement could overcome. Experiments showed that certain pairs of physical properties could not be simultaneously known with arbitrary precision. Increasing accuracy in one inevitably reduced accuracy in the other. This was not a practical inconvenience caused by imperfect tools. It was a structural feature of reality. The more carefully one looked, the more the universe resisted complete disclosure. Precision itself came at a cost, and that cost was not negotiable. Within this emerging understanding, fresh Niels Bohr emphasized that these limits did not signal failure, but coherence. Nature was not hiding information maliciously, it was enforcing consistency. If all properties could be sharply defined at once, contradictions would arise. Stability itself depended on restriction. The universe protected its internal logic by preventing total access. What appeared as uncertainty was, in fact, a safeguard against inconsistency. This realization redefined the meaning of explanation. To explain a phenomenon no longer meant predicting an exact outcome, but describing the range of possible outcomes and the conditions under which they could occur. Probability became fundamental rather than provisional. Events were not unpredictable because something was missing, but because the structure of reality allowed only probabilities, not certainties, to be assigned in advance. This shift demanded a new kind of intellectual humility. Classical science encouraged the belief that enough knowledge would eventually dissolve all uncertainty. Quantum theory denied this hope. Some limits were final, not temporary. This did not diminish the power of science, it clarified its scope. Science could describe nature with extraordinary accuracy, but it could not eliminate indeterminacy where nature itself was indeterminate. The acceptance of these limits had practical consequences. It changed how experiments were designed, how data were interpreted, and how theories were evaluated. Success was no longer measured by the elimination of uncertainty, but by the precise accounting of it. A good theory did not promise certainty, it specified exactly how uncertain predictions would be, and under what conditions. This marked a profound maturation of scientific reasoning. At a deeper level, this understanding reshaped the relationship between cause and effect. Classical causality assumed a chain of events unfolding inevitably from initial conditions. Quantum behavior replaced this with a framework of constraints and probabilities. Causes did not determine outcomes uniquely, they shaped distributions of possibility. Reality became less like a script and more like a rule-bound game, where outcomes were limited but not fixed in advance. This was unsettling because it challenged deeply ingrained intuitions about control. If the universe itself does not guarantee exact outcomes, then certainty is not a birthright of knowledge. Bohr argued that this was not a defect of understanding, but a revelation about the nature of existence. The demand for absolute certainty, he suggested, was a projection of human desire, not a requirement of reality. Importantly, this acceptance did not open the door to chaos or arbitrariness. Quantum laws are among the most precise ever formulated. They constrain possibilities with mathematical rigor. What they deny is not order, but inevitability. The future is structured, but not predetermined in detail. This subtle distinction allowed physics to remain predictive without pretending to omniscience. By recognizing the limits of certainty, science gained a deeper form of reliability. It stopped making promises it could not keep and began articulating exactly what could and could not be known. This honesty strengthened the credibility of scientific knowledge rather than weakening it. It aligned explanation with reality instead of forcing reality to fit expectation. This legacy continues to influence how modern science approaches complex systems. It serves as a reminder that understanding does not always mean removing uncertainty. Sometimes it means mapping it carefully and accepting its necessity. In this sense, the quantum revolution taught that the strength of knowledge lies not in absolute control, but in disciplined respect for the boundaries nature sets. As the quantum revolution reached maturity, its most enduring lesson was not a formula or a prediction, but a transformation in attitude toward knowledge itself. The early hope that physics would eventually provide a complete, final description of reality began to fade. In its place emerged a more demanding insight. Understanding the universe requires accepting that some questions cannot be answered in the way they are asked. The future of physics would not be built on the promise of total clarity, but on the discipline of recognizing limits. This shift did not arise from philosophical speculation alone. It was forced upon science by relentless experimental evidence. Every attempt to push beyond certain boundaries produced not deeper certainty, but contradiction. The more physicists demanded a single, unified picture of microscopic reality, the more nature resisted. What initially felt like a failure gradually revealed itself as guidance. Reality was signaling how it could be approached without distortion. Within this realization, Niels Bohr articulated a vision of science grounded in humility rather than dominance. He argued that the goal of physics was not to reveal how nature is, in itself, but to clarify what can be said about nature under specific conditions. This distinction was subtle yet profound. It replaced the idea of absolute description with the idea of communicable knowledge. Science became less about uncovering a hidden script and more about establishing reliable relationships between observation, concept, and outcome. This humility did not weaken physics, it strengthened it. By accepting limits, science avoided false certainties and conceptual traps. It learned to move forward without demanding metaphysical closure. Theories were judged not by their ability to satisfy intuition, but by their consistency, precision, and respect for experimental constraints. The future of physics became an open process rather than a destination. This attitude also protected science from dogmatism. Classical physics had once seemed complete, only to be overturned by discoveries it could not accommodate. The quantum experience served as a warning against repeating that mistake. Any framework, no matter how successful, might have a domain beyond which it no longer applies. Recognizing this possibility became a mark of intellectual maturity. Progress was no longer defined by final answers, but by increasingly refined questions. The consequences of this shift extended beyond physics. It influenced how scientists thought about explanation in general. Instead of reducing phenomena to a single cause, they learned to describe systems in terms of constraints, contexts, and interactions. This approach proved especially powerful in complex domains where linear causality breaks down. The quantum lesson, that understanding often requires multiple, limited perspectives, became a guiding principle across disciplines. At a deeper level, this transformation altered humanity's relationship with the unknown. Mystery was no longer treated as an enemy to be eliminated at all costs. It became a feature of reality to be approached with rigor and respect. Not all mysteries are problems awaiting solutions. Some are boundaries that define the shape of meaningful knowledge. Accepting this distinction prevented science from overreaching and preserved its credibility. The future envisioned through this lens was not one of resignation, but of disciplined exploration. Limits did not signal the end of inquiry, they defined its structure. By knowing where questions lose meaning, science could focus its efforts where clarity was possible. This selectivity made progress more efficient and more honest. This perspective also carried an ethical dimension. The desire for total control, whether over nature or knowledge, often leads to distortion. By acknowledging limits, science modeled a form of responsibility. It demonstrated that power must be balanced by restraint and ambition by awareness of consequence. In this sense, the quantum revolution offered not just a new physics, but a lesson in intellectual character. Looking forward, this legacy remains vital. As science confronts increasingly complex systems, from fundamental particles to living organisms and conscious minds, the temptation to oversimplify remains strong. The lesson learned at the quantum frontier stands as a safeguard. Understanding grows not by forcing reality into familiar categories, but by adapting categories to reality, even when that adaptation is uncomfortable. The enduring impact of this revolution lies in its redefinition of success. Success is no longer measured by the elimination of uncertainty, but by the clarity with which uncertainty is understood and communicated. Knowledge becomes reliable not because it is complete, but because it is honest about its scope. In embracing this vision, physics secured a future that remains open, flexible, and resilient. It learned that the deepest form of understanding does not come from claiming final answers, but from cultivating a respectful dialogue with a universe that is richer than any single description.